Okay, today we're going to be learning about stacks and queues. Um, I think this is like lesson 4 or 5. I don't remember. uh, a stack. So basically, a stack it goes by the rule of LIFO, last in, first out. The last element added is the first one removed, which makes sense, right? So it supports two operations: push, which adds an element to the stack, and pop, which removes the top element from the stack. So let's say you have an empty stack here. I don't know if you can see my mouse. This might be better. You have an empty stack here. You push 1 in, and then you push 2 in. You can pop 2 out, and and like because it's a stack, you can only access like the uh top character or whatever you have a stack of. You can pop that one out, and then the next to pop out would be the one. Stack implementation. So this is basically code on how to use a stack. Here you have the declaration, which is stack with a type string. So the stack contains strings, and it's just called stack and new stack, blah, blah, blah. Yeah, it's very similar to an array list. Stack.push cats, stack.push dogs. Who's on top? Check without removing. To check without removing the previous character added, you can just stack.peek to see on the top, and to take out the elements, you can do stack.pop. And since dogs is on top, dogs are first, and then secondly, cats are second. Here's method summaries. This is the API. You have .empty, .peek, .pop, .push, and .search, and return each of you can .empty tests if the stack is empty. So if you have nothing in there, it's going to give you true, I think. And .peek looks at the top object. We talked about that. .pop, it pops out the first object and returns the value. Yeah. .push, it pushes an item onto the stack. So basically adding an item to the top. And .search returns the one base position where an object is on this stack. Makes sense? And this is a question which uses stacks. It's called zero that out. The problem statement is basically summarized into this. Your boss says numbers, and you have to keep track of those numbers. Whenever your boss says 0, however, you have to remove the last number he said. And basically the end question is, what is the sum of the remaining numbers? So boss statements, you have 1, 3, 5, 4. Yeah, those are your current numbers. And then he says 0, 0. You have to remove 4 and then remove 5. And then he says 7. You have 1, 3, 7. And then he says 0, 0 again. You have 1. And then you have 6. And then that's your answer, basically. And you just add the sum of the remaining numbers, and that's how you get 7. Visualization, zero that out. So boss instruction, add 1. Add 1 to the stack. Boss instruction, add 3. You add 3 to the stack. Boss instruction, add 5. You add 5 to the stack. Boss instruction, add 4. You add 4 to the stack. And then your boss says 0, so you have to remove the last number. So goodbye 4. And then he says 0 again, so you remove another number. And then he says 7, so you add a 7. Then he says 0 again, and then 0 again. And then he says 6 at the end. So that's how a stack works. And the sum is 6 plus 1, you'll get 7, right? And so this is a simple solution, not coded by me. Congratulations, Ryan. So you see, you take the input here, basically taking in the number of numbers that your boss says. You declare the stack. You take in the input on each line, and if it if the input is 0, then you dot pop the previous number, and else you add the number to the stack. And here at the bottom, you just simply add up everything within the stack, and then you print it out. You print out your sum. Here's the replit I guess he made. I didn't actually know that was a link. The code's there. I don't have the input with me right now, so I cannot cannot show you that. But yeah, just trust me, this works. And here's another CCC question that uses stacks. It's called the Geneva Confection. The problem statement is that there are carts numbered 1 to n that are lined up at the mountain top. We can either 1, slide it out of the branch and then into the lake, or slide it straight into the lake. We can slide the carts into the lake so that cart number 1 ends up in the lake first, cart number 2 ends up in the lake second, etc. So basically, you need to slide these into a branch and then like organize them in a way so that they get into the lake numbered 1, 2, 3, 4, like that. Basically, organizing the carts. And so, if you look at the branch where you can store your carts, it's basically a stack. It's a branch. Yeah, the branch is a stack where you can keep your stuff and like pop it back out and stuff. Basically, just you can use a stack as the branch. And so the start, you have 2, 3, 1, 4, and then 4 you insert it into the branch, which is stack.push 4, and then your next number you need to get into the lake is 1. Now you have 1, since you just moved 1 straight to the lake. You need to get 2 to the lake, but that's stuck up there. How do we do that? You push 3 into the branch, stack.push 3, and then you push 2 into the lake. And then now from the branch, you can push 3 out, or stack.pop, and then you can do stack.pop again, and then 4 will come out of the branch, and you'll have 1, 2, 3, 4 lined up in the lake. And so this is a solution written by Ryan again. Congratulations. The input is given in reverse order, so add all the numbers into a stack, which is basically what he does. Yeah, he does. He takes the input and then mountain.push in.next int, yeah. And then if the first cart of either the mountain or branch corresponds to the next number into the lake, dump it into the lake, which is wait, Ryan, can you explain your own code? I'm having trouble.
Oh, okay. So it says while next is less than n plus 1, which means that not all the carts have been added into the lake yet. So if that's the case, then we check if mountain is empty. Because if mountain is empty, then we don't have to check mountain, or else .peak would throw an error or something. So if the cart from the mountain, like the first cart from the mountain, is equal to the next number that has to end up in the lake, then you would pop it from the mountain and increment the next variable, which means that basically means that you just added a cart into the lake. And we also check if branch.peak equals next, which means the first cart in the branch. Is it the next number that we need? If it's not, then if it is, then we can pop it. But if the next number in both the mountain and the branch do not correspond to the number that needs to end up in the lake, then the configuration is impossible, and you would just break out of it. And if it's complete, then you would print out yes. Otherwise, you would print out n for no. Yeah, basically.
These are some stack problems. We explained zero that out in the Geneva Confection. From prefix to postfix is another one, but we don't explain it in the slides. You can go do that one yourself if you want to. Good joke.
Oh, I can start screen sharing now.
Yeah, I forgot about that. Stop share. Yeah.
Okay. All right, so Jake talked about stacks, and now we're going to talk about queues, which is kind of like the opposite of a stack, if you think of it that way. A queue is different from a stack because it's FIFO, which means that the first person who went into the first thing that's added to this data structure is the first one that's going to come out of this data structure. So you can think of it like a line. The first person who ends up in the line would also be the first person who leaves the line if we're using the first come, first serve method, right? Which is basically what FIFO is. You would add people at the back of the line and you will remove them from the front of the line. So that's an application of a queue. And you can only view and remove the element in the front of the line. And you have two operations for a queue. So you have offer, which adds the element, and you have poll, which removes an element from the queue. So offer, you can give any element into the queue, and poll just removes the first element from the queue. Okay, so to talk about the different methods, if you do offer, then it would add an element to the queue, and you would put the element in between these brackets. If you want to see who's at the front of the line, you can use peek, which returns the first element. And if you want to get rid of the first element, then you would use poll, and it'll also return the object that's in the front of the line. So that's just a summary of all the queue methods. You can also use add, remove, and element, but these ones would throw an exception, which means that your program would crash. And if you do offer, poll, or peek, and that object is not there, it should return null. And this is just an implementation of a queue. So these are poorly drawn drawings of me, Jake, and Jerry. So we can be represented by our names. And so I can make a queue. So what I have to do first is I have to import java.util.queue. And I also have to import java.util.linkList. And what I do is I can initialize a queue using a very similar method as stack. I would just do queue and the data type here and the name of the queue equals new linked list. And I can add things into the line by using the dot offer method, which adds things in the back. So I would add J. So this is how we can implement a queue. So that's how we initialize a queue. And we can add elements into a queue using the dot offer. And we would just put that element in between the brackets. And if we want to see who's first in the line, then we would use line.peek, which prints out Jake because Jake was the first object that was added into the queue. And then we can use the dot poll method, which would remove the object and print it out. So Jake was first, so he's going to get removed and printed out first. Ryan was second, and Jerry was third. So that's how we can use a queue. There aren't too many practical applications of a queue in competitive programming so far with what you've learned so far. But once you learn some more advanced concepts, queues can come in very useful. And another thing that's probably new to most of you is a hash set. So a hash set is basically a collection of unique elements. It's a data structure that holds a lot of different elements, but no two things can be the same. So you can use this when you only need to know whether an element is in a group or not. So I can make a hash set that's called school, right? And I can add like strings into it. And I can check, is troll aka troll inside the hash set? And it'll tell me like a Boolean, true or false. I can check if I'm in a hash set that's called club. And if I'm not in the club, then it'll return false. So you can add things into the hash set and you can check whether certain objects are inside the hash set. And it's guaranteed that all the elements within a hash set are unique. That means I can't have, for example, if I'm having a hash set of numbers, I can't have two identical numbers inside a hash set. The order is random, and there's no indexing, like an array or like an array list. So for example, I created this Pokemon hash set. And you can check whether if certain Pokemon are inside the hash set. Yeah. So these are the methods that are associated with a hash set. So you can add things into the hash set. You can clear all the elements in the hash set. You can check if it contains a certain element. You can check if it's empty. You can remove a certain object from a hash set. And those are all the methods you need to know about hash sets. So this is an implementation of HashSet. So let's use a hash set that's called pets. And we're going to put people who go to pets in there, right? So we're going to add Jake into it. We're going to add Ryan into the hash set. And we're going to try adding Jake again. But this really does nothing because Jake is already in the hash set. And the hash set cannot have duplicates. So this would, in effect, do nothing. And we can check the size of the hash set. So this prints out 2 because there's only Jake and Ryan. It can't have a duplicate. So this line had done nothing. We can check if Jake is in the hash set, and this would print out true because we added Jake earlier. We can also check if it contains Dawn, but it prints out false because Dawn is not in the set. And we can also remove elements by specifying the element that we want to remove from the hash set. So this line would remove Jake, and this line would do nothing because Dawn does not exist in the hash set. So these are some hash set practice problems. I'm going to live solve this one. So just so you guys can get a hang of solving set problems. Let's see. I'm just going to share my screen instead. So it gives me a little bit more flexibility. Do you guys see the Dimash problem? Okay, that's great. So this one is pretty straightforward. It's called unique elements. We know it's a set problem because it even says set over here, which is a hint that you usually don't get. So given a list of n positive integers less than or equal to a very big number, print out how many distinct numbers exist. The first line will contain the integer n, and it tells us that's the number of numbers that we have to read in. And we will output one integer, which is the number of unique elements in the given list. So this is a perfect problem for a set because we want to know how many unique elements are there in a data set. So let's see, let's code up the solution. So one way I like to do it is I split it into 2 screens. So I can do this. Okay, so first I need to read in n, which is the number of integers that I have to take in. And I already imported scanner here because the star imports everything that's in java.util. So I'm going to make a scanner. And I can read in an integer. And I have to read in n integers, so I use a for loop for that. And let's call that integer x. Here, what we can do is we can make a hash set. So let's just call it set. And so what we can do is we can add this x into the set. Remember, if we are trying to add a number that is already in the set, it would basically do nothing. Like the size of the hash set will not change at all. So just by checking the size of the set at the end, we can find out how many numbers are unique. yeah, so this problem was relatively straightforward. We just make a scanner, we make a hash set, we take in the number of numbers and use a for loop to read the input. And we're just adding all the numbers into the set. And duplicates would just be ignored because the number is already in the set. And then we can get the number of unique numbers that was in the data set. So let's submit this and see what we get. Yay, we passed all the test cases. So yeah, so this is a very efficient way of doing it. Okay. Let's try this problem. This one's not on Dimaj, but it's a problem that's called spell check, and it also you have to think a little bit more about how you can use a hash set in this problem, but you'll see it's relatively straightforward. So after the spike in unemployment in Canada post-COVID-19, Nicholas can no longer afford his premium spell checker subscription, which is totally not Grammarly. Luckily, Nicholas has kept a spelled correctly just for this occasion. If Nicholas gives you his word list and a sentence of M words, can you make a program that helps Nicholas find his mistakes? The first line contains two space-separated integers n and m. N is the number of words in Nicholas' dictionary, and m is the number of words in the sentence. And we would need to output a single line containing a space-separated list of the positions of misspelled words. So the first word would have index 1. For example, in this sample input, we see that there's 8 words in his dictionary, and he wants us to check a sentence that has 9 words. So if there's any words in this sentence that aren't specified in his dictionary, then it would be perceived as incorrect. So does anyone have any ideas on how we can use a hash set to find out which words are wrong here? So whichever words that are in the lower sentence that aren't in the top sentence would be considered wrong. So how can we use a hash set to solve this problem? So I can run through an example. So for example, let's check this. Is this in the top sentence? Yes, it is. So this is a correct word. Is in the top sentence? Yes, it is. It's right here. Is a correct word? Yes, it is, because it's right here. Is properly a correct word? Yes, it is, because it's been specified in the dictionary. Is spelt a correct word? No, because it wasn't mentioned up here in this first sentence. Then what we would do is that we would print out its position, which is 5, because it's the 5th word in the sentence that we're checking. And this sentence is wrong because it's not specified in this top sentence. Yeah, so how can we use a hash set to check if these words are correct? Any ideas? Maybe I can word it in a different way. So we're seeing if this top sentence contains this word. So what's something that we can do? We check if this thing contains this.
Any ideas in the chat? Ryan.
Yeah, so basically you would put, yeah, so Andrew is right. We would just put all of these words up here into a hash set. And then we would go word by word down here and see if the hash set contains this word. If it does, then great, it's a correct word. If it doesn't, then you would print out the index. So let's try coding this out. So very similar to Dimage. So let's do that. Let's make a new tab. Let's drag it over here. So first we would read the number n, which means the number of words in Nicholas' dictionary. And we will need to make a scanner first. So we would do in.nextInt. And m, which is the number of words in the sentence that he wants to check. So m. And then we have to read all the words in his dictionary. And this we want to keep in a hash set because we want to check if it's correct. So these are the correct words. Keep it in a hash set. So let's read our string, which is in.next. And let's do correct add as. So we're adding all the strings into the hash set. And then we have to read in the sentence. So we can make it into an array so we can find out its position. Honestly, we can just do this, try that. And let's read in the string. And we want to check if that string is in the hash set. So we do if correct.contains s. So is this word, was this word added into the correct dictionary, has all the correct words? We want to check that. So if it doesn't contain it, so equals false, then we would print out its position. Print I plus 1. Because it starts from 1, but we start from 0 here. So we can do I plus 1. And we want to add a space to it. So, and then we can print out a new line. And hopefully this works. Yeah. So what we did here is we added all the correct words into a set. And here we're just checking if the word that we're considering is in the set of correct words. And yeah, it could do this really efficiently, like very efficiently. So that's why we like to use HashSet instead of keeping it into a list, because that would take a really long time. So let's try submitting this. Oh, yikes. What did I do? Oh, wait. String. Did I accidentally? Oh, integer. What? Should be a string. I just got so used to like using integers instead of strings. This is so suspenseful.
You're gonna get a TLE or something.
I hope not. I think this is the intended solution for this problem. I think it's just my Wi-Fi, honestly.
It's probably
page is
your
loaded.
Wi-Fi. You crashed out of the Zoom meeting.
Yeah, I know, right?
But Yay, we have 13 out of however many test cases
Yeah,
were
okay,
correct. Let's just pretend he got it correct.
yeah.
And yay, he solved the question.
Yay, I solved the question. Probably. I probably solved the question. Yeah.
Questionable name.
Okay. It's going to take a while to load. Does anyone have any questions about how to use HashSet? So as you can see here, there were two uses of HashSet. One, you can use a HashSet to check how many unique elements are in a data set. And two, you can use HashSet to check if a word is part of a set or if a number is part of a set, right? So you can check if an element is part of a group using a HashSet. And it does this really quickly, as long as you don't have bad Wi-Fi. Yeah. Mm. And okay, let's see. And then there's this question, which is quite nice. So it looks really intimidating. See, like, what is this DI thing? What is this N thing? What is this I thing? All right. What is D1, D2, DN? Why is this a three-pointer? Yeah, so let's go through this problem. So you're planning to run N programming contests in the next few weeks, but you quickly realize that you've bitten off more than you can chew. As a novice problem setter, you quickly learn that the rumors are true. Indeed, original and interesting problems are indeed really hard to write. Fortunately, you're not alone in this contest writing endeavor. Your friend is here with you. However, you know deep down that in order to be credited with creating the contest, you just need to supply a single problem for it. You know that your friend will take care of the rest, even if it means that he'll be very angry for having to do the remaining work. The contests are numbered from 1 to n, and you've agreed that in the IVE contest, you must contribute a problem of difficulty level DI. You don't want to do a lot of work, so you want to create as few problems as possible to get the job done. And you want to repeat problems when multiple require problems of the same difficulty. And surely no one will notice. So you would focus solely on making problems for the next few days. You're able to make an original problem of any difficulty level if you try hard enough. What is the minimum number of original problems you'll need to write for the end contest? So it says the number of contests that you're responsible for, and you have these integers, which are the difficulty level of the problems you have to contribute for the contest. So basically what this question is asking is that you have multiple contests that you need to create problems for, but you want to minimize the number of different problems you want to make. If there's one difficulty level, you only want to create one problem for that difficulty level. You don't want to do repetitive stuff. So for example, if I have two contests I need to write, and they're both the same difficulty level, I only want to consider one. I'm only going to make one original problem. So what does that sound like? When you have two contests of the same difficulty level and you only want to write one. So like for here, maybe this would be a clue. So contest 1, I need to create problems of difficulty 3. And for contest 2, I need to create problems of difficulty 2. For contest 3, hell nah, I'm not going to write a new problem. I already wrote a problem that has a difficulty level of 2. Why am I going to write a new problem for this? No way, I'm really lazy. So I'm not going to do anything because I already wrote a problem of difficulty level 2. How about a problem of difficulty level 1? Oh no, I haven't written this before, a new problem. For contest 5, I need to create problems of difficulty level 3, right? But I already wrote a problem of difficulty level 3. I'm not going to write it again. And for the last contest, I need to create problems of difficulty level 3. But I already created problems of difficulty level 3, and I'm really lazy, so I'm only going to use the original problem. And I'm not going to create a new problem. So in the end, I only need to create problems of difficulty level 1, 2, and 3. So how can we do this? Yeah, so Andrew got it right again. Yay. You would just make a hash set of all the difficulties. Technically, you don't need a hash set because there's only 1,000 difficulty levels, and you can use a Boolean array. But in future problems where the numbers can get really big, then that's when you can use a hash set. So yeah, so let's try this. This is basically the same problem as the unique elements problem that we did earlier. We're just putting all of these into a set, and we're printing out the size of the set. So usually they would be very clever. They're going to hide like a really easy problem, and they give you all this text, make you feel like very demoralized. But in the end, you realize the solution is actually very simple. So, so sets can be really useful in these two applications, counting the number of unique elements and checking if something's in a group of things. Yeah, I'm not going to cover this problem because this problem, at most, you can get like partial points, which is not, you cannot like solve it just using HashSet. Yeah, so I encourage you to try this problem setting pandemonium problem on your own time and let me know how it goes. So what did you learn today? You learned about stacks, which are last come, first serve, queues, which are first come, first serve, and hash sets, which are random collections of items where you can check if something's inside it, and you can check how many unique elements are in a data set. Yeah, that's pretty much it for today's lesson. It was pretty short. And these are our social media accounts if you want to follow them. We're usually more active on Discord, so if you're not there, feel free to join the Discord. And yeah, that's the end of today's lesson.